Hey everyone, Mr. Calc here. In this set of notes, the 9.6 notes, we're going to be looking at, we're going to be starting basically the polar section of this BC only unit. This should be pretty quick and easy for this set of notes because previously you guys reviewed the different types of polar graphs. If you haven't done that, you need to make sure you do that first. So this should be pretty quick and easy. We don't do any actual calculus today, which is one of the reasons you don't have homework for this set of notes. In tomorrow's set of notes, in tomorrow's video, we're going to actually start the polar calculus stuff, okay? Today is really going to be looking at circles and rose curves as polar functions, all right? So it should be pretty quick and easy, hopefully. All right, so a rectangular coordinate system is only one way to navigate through a Euclidean plane. Such coordinates x, y, known as rectangular coordinates, are useful for expressing functions of y in terms of x. At some point in pre-calculus, whether it was AP pre-cal for those of y'all that took AP pre-cal, or if it was accelerated pre-calculus, some of y'all took a couple years ago, you should have had a part of the course where you learned how to represent polar points, okay? And we have this alternative coordinate system called the polar coordinate system, where instead of x and y, we use r and theta, all right? So in this polar coordinate system, we have what's called the pole. The pole, which is right here, is the origin, all right? The origin is called the pole. We can get to any point in two-dimensional space by specifying an angle theta, then using r to specify the distance from the pole. If r is greater than 0, walk towards the angle. If r is less than 0, use the opposite direction. You'll see what we mean here in just a second. So, in example 1, so this is going back to either AP pre-cal or accelerated pre-cal, whichever one you took. Find two equivalent polar coordinates for the point above. One where r is greater than 0, one where r is less than 0. Okay? We're talking about this point right here. So, first things first, notice that we have these rings, these circles. Okay? So, this point right here, let's take a look at this point. This point, one way we can represent this point is notice that it's sitting on the second circle, so r would be positive 2. And if r is positive, we're saying the second circle here, if r is positive, then we walk towards the angle being pi over 6 radians. So one way for us to represent this point is we could say 2 comma pi over 6. Okay, this is our r, this is our theta. Okay, now it says we want to have two equivalent polar coordinates. One where we use a positive r, one where we use a negative r. Now, I know it's been a little while, but if you think back to AP pre-cal or accelerated pre-cal, if I change r from a positive to a negative number, what you do is you take the angle and you add pi to it. So if I take pi over 6 and I add pi to it, this would be the same as pi over 6 plus 6 pi over 6, which would be 7 pi over 6. So negative 2 comma 7 pi over 6 would be an equivalent polar coordinate. Okay, so if you have a positive r, if you change r, change the sign of r, you get add or subtract pi to the angle. Okay? All right, so polar equations on a graphing calculator. Go ahead and follow these steps in your TI-84. First, press mode, change the highlight from function to polar. So we've already done this with parametric, but now change from function to polar. When you press the y equals button, you're going to notice that you're going to have a bunch of, instead of y equals, you're going to have a bunch of r equals, okay? Also notice that when you press the variable button, instead of putting in an x like it normally does in function mode, it's going to type out a theta instead of an x, all right? Highlight the box in front of R1 and hit enter. Change the line style to the one that looks like a circle with a line coming out of it so that we can graph. You want to do this, change the style to the one that looks like a circle with a line coming out of it so that you can see it trace the graph when you hit graph. Okay? Press the window button. This allows us to change the domain. The calculator is going to default to be 0 to 2 pi. You're going to notice here in just a minute that we don't always want it to be 0 to 2 pi. Sometimes we want to change the theta minimum and the theta maximum depending on the scenario. All right, so take a moment. I recommend you try this, pause the video, and then come back and check. But we want to sketch the following using a graphing calculator, okay? So go ahead and try it, but I'm going to go ahead and sketch these. So the first one here is r equals 2 cosine of theta. And I'm actually going to sketch it without a graphing calculator. I'm going to show you how you can do this just by looking at it. So the first thing I notice here is that this is a cosine, okay? This is the format, by the way, all 4 of these are the format for a circle. Okay, these are all going to graph a circle on your polar coordinate plane. All right, what this is showing is I have a circle with diameter 2, and because it's a cosine, it's going to sit, and it's a positive cosine, by the way, it's going to sit to the right of the pole. Okay, so we're going to have a diameter of 2 circle sitting to the right of the pole. So it would look something like this. Okay, diameter of 2, cosine being the horizontal direction, positive cosine is going to sit on the right side of the pole. So this part, diameter, cosine, horizontal. And since it was a positive cosine, on the right side of the pole, not the left side. Okay, so using that same logic, we can go ahead and try to graph this one without a calculator as well, even though I encourage you to try it with a calculator. Notice it's a cosine. That means it's either going to sit on the right side or the left side of the pole. It's going to have a diameter of 5, and because it's negative, it's going to sit on the left side. So we want a circle, diameter 5, sitting on the left side of the pole. Okay, so 1, 2, 3, 4, 5. We want a circle, diameter 5, like this. Close enough. All right. Now let's look at r equals 3 sine of theta. Again, this is the format for a circle. This time, though, notice that it's a positive sine, positive 3 sine. So this time, we're going to have a circle with diameter 3 sitting above the pole. So diameter 1, 2, 3. We're going to want a circle like that, sitting above the pole. Okay. And finally, right here, r equals negative sine of theta. Sine means it's going to be above or below the pole. Diameter is going to be 1, the implied 1. It's going to sit below the pole. So we want a circle, diameter of 1, sitting below the pole. Yeah, I can do a little better than that. Yep, that's good enough. Okay. Now, again, hopefully you tried this with your calculator. It says try using a graphing calculator. Now right now you should have it set to be theta minimum equals 0, theta maximum equals 2 pi. Okay? If you change your theta minimum to be 0 and your theta maximum to pi, well, first off, if you leave it like this, if you make the minimum 0, the maximum 2 pi, what you should have noticed, so I'm gonna write this down. If theta min is 0 and theta max was 2 pi, you should have noticed that it traced the circle twice. Trace the circle twice. If theta minimum is 0, but theta max is 1 pi instead of 2 pi, traces the circle once. Okay, so what this means for us, for a circle, we only need a max theta of pi, 0 to pi, to get the full picture. Okay, if you go 0 to 2 pi, it's going to make your picture twice. All right. Example 3. What is the R value of a point at the pole? Okay. At what angles between 0 and 2 pi? Notice, by the way, that 2 pi does not have the or equal to sign. So what angles from 0 to 2 pi, 0 included, 2 pi not included, will the following graphs be at the pole? Use a graphing calculator to visually verify. Okay, so what does it mean for a graph to be at the pole? This means R equals 0. Okay? R is like that distance from the pole. Okay? R specifies the distance from the pole. I should probably actually highlight that. Okay? R specifies the distance from the pole. To be at the pole, your distance from the pole should be 0. Okay? Hopefully that makes sense. So what we want to do is, for each of these 4, we want to set R to be 0 to simulate being at the pole. And we want to find the angle theta for each of these different scenarios for which we are at the pole. Okay? So let's go ahead and do that. For example A here, 0 equals 2 sine of theta. We want to be at the pole, so we replace R with 0. Then we would go ahead and divide both sides by 2. Now we have 0 equals sine of theta. And from 0 to 2 pi, well, what angles is the sine value equal to 0? Well, that would be 0, pi, and 2 pi. Okay? When theta is 0, pi, and 2 pi, the sine of all those angles is 0. However, keep in mind, 2 pi is not included. We don't have this or equal to sign here. So, we don't include 2 pi. These are our 2 answers. 0 and pi. All right, part B, same deal. We want to know, when will the graph be at the pole? Graph is at the pole when R is equal to 0. Let's go ahead and subtract 1 from both sides. Then we'll go ahead and divide both sides by 2. Okay, now we want to know, all right, well, when is the cosine of theta equal to -1/2? This is just unit circle knowledge. This is when theta is 2 pi over 3 and 4 pi over 3. And we stop there. We don't want to go. The next one would go beyond 2 pi. Example C, same deal. When are we at the pole? We're at the pole when r is equal to 0. Go ahead and subtract 2 from both sides. Right. And now it says negative 2 equals cosine of theta. It's not possible for cosine of theta equal negative 2. Remember that cosine of theta is restricted from negative 1 to 1. So, no solution. This is never at the pole. And I would encourage you to graph this. So by the way, the only reason I'm not going to graph this in Desmos here, if I try to leave GoodNotes, if I try to leave this screen, for some reason my recording stops. So on a separate screen, you can either use your TI-84, I would recommend that. You can also use Desmos if you change Desmos to polar mode. But go ahead and graph it. Graph, r equals 2 plus cosine of theta. And you'll notice your graph never actually touches the pole. So your graph is never at the pole. All right, next example. Same deal. When are we at the pole? Well, that's when r is equal to 0. Let's go ahead and subtract 2. Let's go ahead and divide 2. Right. And then sine of theta is equal to negative 1 when theta equals 3 pi over 2. Right. Hopefully all that's making good sense. Okay, for the next ones. Now we're going to be looking at rose curves. Notice that inside of each of these pair of parentheses, we have something multiplying to the theta. Again, you should have already investigated this in the previous thing you did before the break, where you were looking at different types of polar curves. We have something of this format where we have something multiplying inside to the theta, like this, no additional, addition or subtraction. We know that we're going to get a rose curve. Okay, so these are going to represent different kinds of rose curves. So go ahead and graph them. Take a moment to graph them. I'm going to go ahead and graph them to the best of my ability. They're probably not going to look perfect, but let's go ahead and try it. So 3 cosine of 3 theta, if you were to graph this, would look something like this. And again, if you are using your TI-84, you even get to see the pathway that it takes. The pathway that I'm drawing is not the same as the pathway that it takes. All right, so we get something along those lines for this first one. R equals 2 sine of 5 theta, we get something like this. Again, not perfect, but you get something close to that. 4 cosine of 7 theta. 1, 2, 3, 4. Kind of guesstimating where these different points would be. Yeah, something like this. Again, the pathway that I'm taking is probably not the pathway your calculator is showing you. Alright. 3 sine of 2 theta. You get a little bit more interesting here. Alright, 2 sine of 4 theta. And then 4 cosine of 2 theta. Okay. So, hopefully you went through and graphed those. You get something similar to what I have here. Now let's talk about a couple things that are very important for these Rose curves, okay? These are called Rose curves. So what effect does the coefficient of the trig function have? So look at all 6 examples, coefficient being the number out front. If you look at them, pretty easy to tell. The coefficient is showing the length of the petal. Okay, in this example, when the coefficient was 3, notice that 1, 2, 3 R is 3 here. Okay, that's the length of these petals. When the coefficient was 2, notice that the length of the petal was 2. Alright, same deal for when the coefficient was 4. Length of the petal was 4. Alright, so length of petal. Or you can call it a leaf. Usually I call it a petal. Okay. Now, the more interesting part is what happens when for the coefficient of theta. So what's multiplying inside with theta? Notice that when the number is odd, 3 theta, 5 theta, 7 theta, that if the number is odd, that odd number represents the number of petals. Okay? So, if the number in front of theta is odd, the number of petals will be the same as that number, the same as that coefficient. However, when the number in front of theta is even, so say this was right here a 4 theta, notice that instead of 4 petals, it creates 8 petals. 1, 2, 3, 4, 5, 6, 7, 8. Okay? When this number in front of theta was 2, it creates 1, 2, 3, 4. So when the number in front of theta is even, you get double that coefficient number of petals. Also notice, and you might need to go back and pay attention to the tracing, if the number in front of theta is odd, okay, if the number inside the parentheses in front of theta is odd, you only need a domain of 0 to pi to complete a full graph, to produce a full graph. However, when the number in front of theta was even, you need a domain of 0 to 2 pi to produce a complete graph. All right, last little section. At what angles between 0 and 2 pi, again, notice that 2 pi is not being included, will the following graphs be at the pole? So now we just have, now these are rose curves that we're setting r to equal 0. Okay, again, b at the pole, this means r equals 0. Because r is that distance from the pole. So if r equals 2 cosine of 5 theta, so this would be a rose curve where the petals have a length of 2, odd number in front of theta, that means there's going to be 5 petals. So at what angles would we hit the pole? All right, so 0 equals 2 cosine 5 theta. Go ahead and divide both sides by 2. 0 divided by 2 is still 0. Okay, and we want to know, well, when is cosine equal to 0? Well, we know cosine is equal to 0 at all of the odd pi over 2's. Pi over 2, 3 pi over 2. If you continued, 5 pi over 2, 7 pi over 2. So that means that 5 theta, the thing that's inside the cosine, is equal to all those pi over 2's. I'm actually going to flip this around. So this is the same thing as saying cosine of 5 theta equals 0. Same deal. So 5 theta, we know cosine is equal to 0 at all those odd pi over 2's. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, ... Okay? Now this is for 5 theta. We want to just solve for theta, so we divide all these by 5. So this means theta equals pi over 10, 3 pi over 10, 5 pi over 10, 7 pi over 10, 9 pi over 10, 11 pi over 10, 13 pi over 10, 15 pi over 10, 17 pi over 10, 19 pi over 10, 21 pi over 10, ... Okay? Now remember, our cutoff, it's 0 to 2 pi. So we're cutting off right here. Okay? So anything beyond that 19 pi over 10 is no good. And some of these we can simplify, like the 15 pi over 10, that's 3 pi over 2. The 5 pi over 10, that's pi over 2. You could simplify those. All right. So at all these different angles, that means your graph, again, and when you go and graph it in your TI-84, it shows you the path that it's taking. Every time it's hitting the pole, like when that angle is pi over 10, it's going to come back around and hit the pole. At 3 pi over 10, it's hitting the pole. At pi over 2, it's hitting the pole. And so on and so forth. All right. Same deal for this one. We'll do this one a little bit quicker now. So when will 3 sine of 2 theta be at the pole? Well, 0 equals 3 sine of 2 theta. 0 equals sine of 2 theta. Same thing as saying sine of 2 theta equals 0. So sine is 0 at 0, pi, 2 pi, 3 pi, every pi. Right? So that means 2 theta is 0, pi, 2 pi, 3 pi, 4 pi, ... But we want for theta, not 2 theta. So we divide all those by 2. 0 divided by 2 is still 0. Pi divided by 2 is pi over 2. 2 pi over 2 is pi. 3 pi over 2. 4 pi over 2 is 2 pi. But we cut off here for the same reason. 0 to 2 pi, 2 pi 9. Let's box all these. All right. Then lastly, pick any 2 sequential angles and graph the curve using these angles as your theta minimum and theta maximum on your graphing calculator. What does this produce? So remember that these 2 examples here are both examples of Rose curves. It turns out, pick any 2 of these angles where r is equal to theta. Pick any 2 of them that are next to each other, like pi over 10 and 3 pi over 10. If you pick any 2 that are next to each other and make the lower one your theta minimum and the bigger one your theta maximum, and you go to graph with this is your theta min and this is your theta max, it'll only produce a single petal of the Rose curve. Okay? This creates one petal of the Rose curve. This is going to be important for us in the future, in the next set of notes, when we try to find something like the area of a single petal of a Rose curve. We would want to have, 2 sequential angles where r is equal to 0 to be our upper and lower bounds of an integral, for example. Okay, but that'll be a topic for the future. All right, hopefully this all made sense. Hopefully it was most of a review because you've already reviewed your types of polar curves, and hopefully you enjoy this set of notes with no homework.